talk will be about the research project, so not so much an introductory lecture as I gave before, but about current research I've been conducting together with Silvana Jut. The respective paper actually just appeared in a German journal which is called Soziale Welt, but it's in English, and I think you can download it somewhere at the website of this workshop. It's a special issue on experiments in the social science, or especially in sociology. So, and the talk is largely based on that paper. So if you look at current research about social norms and norm violations, you see there is a paradigm which uses basically a concept, an experimental concept where norm violators are known, like the studies by Yamagishi or by Ostrom, Walker and Gardner, and maybe most prominently by Fair and Gechter, which has been discussed before already. And just let me discuss it briefly. So that's a setup where you have a collective good problem, and in the first stage you can decide how much to provide to a collective good. And in the second stage you get known who of the three other team members, if you wish, contributed how much, and you can punish each of these persons, and you know exactly what everybody did. And so norm violations, so defection is known to everybody. And then you see with punishment an increase in cooperation rate, and without punishment, decrease in cooperation rate. However, it may be the case that actually in reality also there are many situations where norm violators are not known. So, and then you have a detection problem or an inspection problem. So there are many examples like plagiarism, fair dodging. You may think of anti-doping norms in sport, or even an output restriction norm in school, where it is not known how much every school pupil did actually. So the crucial thing is actually to find out the cooperation level of your group members. And so it's not per se given. And there are many other examples like, as I said, anti-doping, tax evasion, fair dodging, moonlighting, plagiarism. We have formal control agencies, but also for informal control, that is the case, I would argue, like output restriction norms that are discussed by Hohmann, two-timing, littering, or maybe even alcohol abuse. So I think that's an important problem when you talk about social norms and reciprocity. And so one model of inspection problems and detection problems is the so-called inspection game. It has been made prominent by Zeveles, for example. And the underlying idea here is that you have two actors. One actor is kind of the target actor of the norm, how Coleman put it once, who can violate a norm or adhere to a norm, and then there's a norm enforcer who can inspect or not inspect. And for inspection there are some costs, so you have to bear some detection costs. And the target actor receives benefits from the norm violation. However, if detected, he receives a fine. So you get a payoff for norm violation and a fine. If the target actor chooses a norm violation, if the norm enforcer chooses inspect, he or she gets a reward for successful inspection. However, also he has to pay costs. And the interesting dynamics of that game is that there is no equilibrium-induced strategies. So if you are here, that you commit a norm violation and the inspector inspects, you get a fine as a target actor, so you choose rather not to violate the norm. However, if you're not violating the norm enforcer has to bear the costs without any rewards. And so the norm enforcer changes strategy, so nobody does anything, and then it becomes again an incentive for the target actor to violate the norm, and then you're again here that the inspector has an incentive to inspect. And so it goes round and round. And so the interesting dynamics here is that it's an equilibrium and mixed strategies. So basically you can look at that when looking at the indifference conditions. So the target actor would choose a probability of norm violation of 1 if he knows that the expected utility is positive. So that, and this depends on the inspection rate Q. And he's indifferent if it's 0, and he will not commit a non-violation if there's a low inspection probability. Likewise, for the non-enforcer, he chooses an inspection probability such that it's dependent on the choice probability of the target actor. So it's 1 if it's, the probability is large that there is a non-violation. It's 0 if the probability is low that there's a non-violation. He's indifferent if that equation holds. And the interesting idea is in mixed strategies that you make your opponent indifferent. And that has the interesting implication that if you raise punishments, there's no effect on thefts or non-violations or on crimes or anything. Because people make the choice contingent on the other person's payoff. And therefore, for higher punishments, there's only less control. And for larger rewards for inspectors, there's less crime. So it goes just vice versa. And I think that's kind of interesting dynamics to study. And I did a couple of experiments on that dynamics, which I would like to discuss now. So first, I gave you an experiment which I've done a couple of years ago, in 2009 published in Rationality Society, but the basic structure is always the same. So the idea is subjects generate an individual income when they come to the lab by using a knowledge quiz. Then they are randomly split half into the roles of players and inspectors. And players can take money from each other, they can commit thefts on each other. And inspectors can invest money to detect theft. And detected thefts generate fines for players and rewards for inspectors. That's the basic setup. It looks like that, so it's kind of for each target actor, there's one policeman, one law enforcer who looks at that because of statistical reasons. So I have data for both roads. So it's kind of a prisoner's dilemma setup that if each other steals from each other, they have less money. So it's kind of a prisoner's dilemma situation if there were no law enforcers, and then you get the inspection game that one inspector or law enforcer inspects the target actor. It's dichotomous decisions, yes or no. And each session is played, there are 5 sessions with groups of 4, 10 sessions total, so there's about 200 people, and it's a stranger matching with a number of periods. And I have mild punishment and severe punishment, which I can compare. Okay. And this is how the data looks like. It's just a sample of the data I'm showing you here. So it is actually the case, if you raise punishments, there's less inspections. So these are sessions 1 to 5. It goes first 50 periods low punishment, then it goes 50 periods high punishment. And you see that if punishment goes from mild to severe, there's less inspection, about 20% less inspection. However, there's also less thefts. So if punishment goes from mild to severe, there's less thefts, about 20% as well, or 30%. And that's very consistent over sessions, over the direction, how you do the effect, or is first severe, first mild. And it's also true if you vary rewards for inspectors, you see a similar dynamics. And so, it seems there's some truth in the story of the mixed equilibria, but it's not completely the case. Like, they didn't match the equilibria. So I had the idea to do a more fine-grained design for inspection games. And this is the longest story I'm going to tell. So the idea is to have not only dichotomous decisions, but kind of continuous decisions. And so the idea was, I put 22 people in the lab, 11 inspectors and 11 target actors who can steal money from each other. And then this is a subsample of this. So we have for each target actor, again, 1 inspector. And there are 10 others, so that's just a subsample. And then each target actor can decide to steal from each other target actor money. And what he can do is he can decide how many thefts he would like to commit. So how many other target actors he would like to steal money from. And then the computer actually randomly assigns which specific target actor is going to be victimized. And so in this example here, it's such that the target actor here is sitting and he decides to victimize 1, 2, 3, 4 people. And the norm enforcer then can also decide how many of the interactions he would like to inspect. And so this norm enforcer decided, this is this dashed line here, to inspect 3, and then the computer randomly assigns these 3, and then 1 is actually detected. That's this interaction here. So 1 out of 3, out of 4. And in this way, one can do a similar design as before with dichotomous choices, but one has a more fine-grained measure. And the idea here is that this allows to get closer to the predicted equilibrium. That was the idea. So what I did, more precisely, is have to, again, 2 conditions. Mild versus severe punishment. It was 50 periods now, not only 30. So it's 25 periods in each punishment condition. It's in both directions, mild versus severe, severe versus mild. It's 10 sessions with 22 subjects each, half players, half inspectors. And that gives a lot of decisions. It's 220 subjects and 11,000 decisions, so a maximum of 110,000 thefts if everybody would steal at every time point. And it's a problem engine. And this design, one can show that this design has kind of the same properties as the dichotomous design. And I will go through that rather quickly, but the idea is that you can calculate the detection likelihood that n out of p thefts are detected by that formula that the norm enforcer chooses q inspections in the target actor p thefts, and then you can calculate sum that up over all and multiply that with n to get the expectation value. If you do that, you get kind of such a picture. These are the detected expectation value of detected thefts for a given number of thefts and a given number of inspections. So if the inspector decides, okay, we'll inspect everybody, it's just the same. So every theft is inspected and detected, and therefore you get the same. And if the inspector decides, okay, I don't inspect anything, nothing is detected, obviously. And so and the middle values are here in between. And from there, you can multiply that with the payoffs. So I give you here the payoffs for the experiment. It's like this. So you have a punishment, and that's the variation I do. So my punishment is 10 euro cent. That has been done in Germany. Or severe punishment, which is 40 euro cent for each interaction here. And then you have a gain of theft of 8 euro cent, that stays constant, and the victimization costs 20. So you also see here the prisoner's dilemma structure behind. But if everybody steals from everybody, everybody's worse off in the end. And then you have the norm enforcer. You can invest in inspection and has to pay 10 euro cent, and if he's successful with a detection, he gets 20. And from there, you get the following expected utilities. So that's kind of the darker it gets, the worse it gets, the brighter it gets, the better it gets. And you see that for severe punishment, if there's a large number of inspections, the target actor would choose not to steal money from anybody. And he's indifferent if there are 2 inspections, and if there are less than 2 inspections, he would get more money the more thefts he or she commits. Likewise, for the inspector or the norm enforcer, it's that dynamics. If there are few thefts, it wouldn't pay off, so it's better not to inspect at all. If there are many thefts, it does pay off, and the difference is exactly at 5 for this combination of payoffs. And that gives a very similar logic than the dichotomous version. So in that, for these values, you see that in mild and severe punishment, one actually will impure strategies, and that's target actors commit 5 thefts regardless of the level of punishments. So mild and severe punishment, because they want to try to make the inspector indifferent, and the indifferent point of the inspector is 5. And for normal forces, it's 8 inspections in mild and 2 in severe punishment. So the same logic holds from a theoretical perspective for that design, but we have much more data points now. And so let's first look at some descriptors to actually take people advantage of this more fine-grained scale. So it could also be that you just do 0 or the full thing, which is predicted by the theory. However, they do take advantage. I mean, this is averaged or computed over everything. So over mild and severe punishments, and you see you get lots of data points with that method. Still, this is theft. Still, most commit either no theft or the full amount of theft of 10, but there's much variation also in between. So there is some benefit of doing a more fine-grained measure. And also inspections, most is 0, but also there is something in between. So I think there is some value in this more fine-grained measure. Nevertheless, if you look at the punishment effects, the picture looks very similar as with the dichotomous choices. So these are the dynamics from the experiment. This here is theft behavior. This here is inspection behavior. Experiment 1 is mild punishment first. Mild is here these light gray dots, and severe punishment is the black dots. And what you see is there's less theft for larger punishments, which is not predicted by this theory, but this simple selfish theory. However, there's also less inspection behavior. So for larger punishments, there's less inspection and less thefts. And you see here the predictions, so it's not so close to the predictions, at least in the direction it's the supposed effect. Okay, and so that gave motivation to me to look at other regarding motives. So this has been the Homo economicus story, if you wish. That's quite also fitting this workshop title. So this is just Homo economicus, purely selfish reasoning behind, and now the idea is, okay, there has been this kind of prisoner's dilemma structure behind, so it may be that there is some reciprocity going on. And the underlying idea is that if you receive many thefts from others, if you're victimized to a large degree, you may actually give it back. That's kind of a generalized negative reciprocity, because you don't know exactly whom you are giving back. Like somebody steals your bike, and then you steal from a random stranger another bike. Something like that. And so we tried to model that using agent-based models. And fitting them to this data set I just presented to you. So, here's a regression if you're interested in that. So, these are learning models. And first, let me explain the self-regarding learners. So here, the idea is target actors try to outplay the norm enforcer. So tries to learn the inspection rate or the detection probability. And so they try to learn the strategy of the norm enforcer and give the best response for a given expected behavior of the norm enforcer. That's the idea. So trying to avoid detection, but try to commit as many norm violations as possible if undetected. So the target actors commit many norm violations if they expect few inspections, and they commit few norm violations if they expect many inspections. And then outplaying is performed as kind of an expected utility maximization. And so the very simplest approach we came up with is you just look at the last period. And if you've been inspected, you don't commit norm violations. If you haven't been inspected, you commit norm violations. That's what we call a short-term self-regarding learning. It's a very short version. And then the longer version is also called fictitious display in the learning and games literature. So basically what we try to do is figure out the detection likelihood from all previous interactions you had, so you compute an average of this, and then you take that and plug it into your utility function, so the payoffs you have, and then you commit as many non-violations as you can if you have a positive expected utility, and you commit no non-violations if you have a negative expected utility. That's the idea behind that. And here is a bit more the formal approach. And so, and this is even more formal, so you can use the indifference points, which I have shown before, to do that. And then using the expected detection probability, you can say, okay, in the mild condition, I won't commit any non-violation if there are more than 8, so that's the indifference point, more than 8 inspections, and I commit as much as I can if there are less than 8. And if it's just at the indifference point, we plug in just the median value, or the mean value, which is 5. And reversely for the severe punishment condition. So you don't commit any non-violations if there are more than 2, and likewise you have the indifference condition and this condition. So that's kind of what a rational player would do if he learns the strategy of the opponent. And then we contrast that with other regarding reciprocators. You see here that you play a kind of tit for tat. And the simplest version is I just give back what I've been given. So you look at the last period, and you just give back the number of thefts you have been given. So the victimization rate of yourself is kind of the theft rate in the next period of yourself. So if you've been 5 times victimized, in the next period you victimized others, 5 others. And more sophisticated is a long-term reciprocator. Then you average of all experiences you had and then give the average back with Romney. Okay, and now we can compare self-regarding and other regarding types in the inspection data. So what we did first is just compute how many we have, so the percentage. So this is relying on, so what we did is we simulated all that, looking at the data, and looked whether what type is fitting best the data we had. And this is using here the short-term learning models, but also for the long-term learning models, it's virtually similar. So we have a large proportion is closest to being a self-regarding learner, and nevertheless, there is about a quarter which can be described as other regarding reciprocators who prefer to give something back regardless of how many inspections they receive. And this is also costly. So here is the final payoffs for types. And self-regarding learners have a larger mean in terms of the final payouts in euros, close to 50. Whereas other regarding reciprocators have a smaller mean, so they pay for being reciprocators. They pay for paying back victimizations by own thefts. And so, how we went on is we tried to understand a bit better, not only with behavioral, but also with attitudinal measures, reciprocity. So what we did is we had a behavioral measure, or an attitudinal measure, sorry, for reciprocity, that's from Perugini and others, a scale. It consists of 9 items, it's negative reciprocity, and basically, if somebody does something bad to me, I give it back. So you have here items like, if somebody puts me in a difficult position, I will do the same to him or her. If somebody offends me, I will offend him or her back, and so on. Here are factor loadings, and we computed a factor score with that. And then this allows us to predict with attitudes and with the strategy, the behavior in the inspection day. And so what I show you here is kind of a graphical interpretation of an interaction effect between attitudes and strategy and their effects on behavior. So what you see here is the number of received victimizations, which are called the reciprocity strategy, from 0 to 10, and the number of committed thefts in the current period. And this is for the short-term learning model, this is for the long-term learning model, and the idea is here now to differentiate for types which come from this attitudinal measure. So we have here the reciprocity attitudes and people who score low, who don't care at all about reciprocity in these items, and people who score largely on this reciprocity, who care largely about reciprocity. What we see from the black diamonds, and this is more or less a tit-for-tat strategy. So if I get victimized a lot in the previous period, I give back a lot of thefts in the next period. So it's really a steep line that's true for the short-term and the long-term learning models. However, if you don't care at all about reciprocity, it doesn't make a difference. So here is the minimum from that scale people have. And you see that regardless of the number of victimizations, your theft target keeps more or less constant. Here it's even negative. And so you see a strong interaction between the attitude you have and the strategy on the behavior. These are the corresponding regression models, but maybe it's a bit too complicated to explain in the last minute. So, conclusions are, there are many examples of non-violations where it's not known who committed it. So that makes it worthwhile studying these kind of games, like inspection games. The inspection game is a useful model, I believe, for such situations. And one contribution of this talk is that I present a novel experimental design for measuring continuous decisions in inspection games and provides very rich data, I believe. So you have thousands of observations you have. And results are, there are more severe punishments, there is less inspection, actually, but there's also less theft. And some part of that paradox, if you wish, may be explained by heterogeneous populations, that some are self-regarding and others are other-regarding. And this may explain some of this variance. And so other-regarding reciprocate respond with more thefts if they're more often victimized, and self-regarding learners respond stronger to inspection than to victimizations. So that's it. Thank you very much for your attention.